Okay, my apologies for accidentally closing that out. That's okay. We'll make this a two-parter. Last time on electrical phenomena, we had discussed how the potential energy of water at the top of a waterfall, as it falls, turns into kinetic energy. And we're making the analogy to a battery. All right. Electrons have a negative charge, so why do they flow out from the positive pole? That should be negative, this should be positive. But when electricity was first studied, they knew something was coming out of here, but they didn't know what it was. So they thought, okay, something coming out that's positive. And this is where it's going to, okay, negative. Later on, when they learned about the structure of atoms, they realized that they designated protons as positive and electrons as negative. Still later, they found out that, oh, gee whiz, the stuff coming out of here is electrons, which are negatively charged. But they already called that the hot pole, so it was too late to change that, so that's just kind of the way it went. So, anyhow, from the positive to the negative is the potential difference. So, just like water falls from a height, turning into kinetic energy, electricity moves from a positive pole to a negative pole. And the greater the potential difference, the more you get the flow there. Now, with a waterfall, the potential difference is literally the height. With a battery, you could have a little thin watch battery that has a higher voltage, and I should just go ahead and say that. Potential difference is measured in volts, named after the Italian scientist Volta. But volts are an electrical phenomenon. The length of the battery has nothing to do with it, like it would with a waterfall. Potential difference is defined as the work per charge, where V is potential difference, volts. W, unsurprisingly, is work, and Q is charge. So, just like the higher the waterfall, the more work the water does, then the greater the work that the charge is doing, the greater the potential difference, the greater the voltage. I'm not going to go too deep into that really. I just want to get the basic concept. This was on page 498 in your packet. So, what I want to do from that point is skip ahead a little bit, get past the section on capacitance, which is admittedly a very important topic if you ever go into electronics, but we're just trying to get to the basics here. What I'm doing is going on to current. So now we're on page 523, current. And as I more or less already said, current is just a flow of electrons, which is equivalent to a flow of charge. So if I had a little tiny mountain creek, I had the Ohio River. Okay. So obviously the Ohio River is much, much bigger than the creek. What you could do, you might put up a little measuring station here at the creek, and you might say that there were so many gallons per second flowing past. And for a small mountain creek, it's probably not even a full gallon per second, probably a half gallon or a quarter of a gallon or what. And at the Ohio River, you would probably have several thousands of gallons per second. So you could compare the flow of a big river and a small creek. Well, current, that's what basically it is. It is charge per second. So if you recall, we measure charge, the metric unit of charge, the coulomb, named after a scientist of that name. So we have a formula. I equals Q over T, where I symbolizes current. Don't ask me why we use I for that, no clue. Capital Q is charge, which is measured in coulombs, and T time, obviously, is in seconds because we are in the meter kilogram second system. So current is measured in coulombs per second, and a coulomb per second is what we call an ampere, named after a French scientist of that name. Although, if you spell his name correctly, there's a grave accent on the first E. So basically, 1 ampere, 1 amp, equals 1 coulomb per second. This is a lot, people. Coulomb is a very large, doggone it, these things keep getting in my way. A coulomb is a very large amount of charge. Um, you may have heard this said that the voltage of something is not what is dangerous, it's the amperage. And that's true. To give you an analogy, if you're standing under a very small waterfall, maybe a very small stream coming off of a mountain, and maybe it's just a few feet up above you, get your hair wet, it won't do much beyond that. And if it's a very, 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 very small stream, maybe just a few cups of water flowing by per second, say maybe this is 6 feet above you, maybe this is 50 feet above you, it's going to hit you harder on the head because it falls farther, but it's not going to really hurt you because it's still not that much water. It would just feel like a very strong shower. But if you stood under Niagara Falls, it is probably going to have a bad effect on you. You will probably die. So the height of the waterfall is analogous to voltage. High voltage, you would notice it all right. Maybe you have seen these things, and Mrs. Sly might even have one. They look like that, called a Van de Graaff generator. They can make thousands of volts, and if you touch it, your hair stands on end. Literally, it tingles, it feels funny, but it's not going to hurt you. Just like you might feel some tingling from the water falling from 50 feet on you if it's a very small stream, but it's not going to hurt you. Amperage, though, is equivalent to how much water is coming through. And if enough water is coming through, it doesn't even have to be that high. If you were standing under a big, big, big waterfall, even if it's dropping, say, 20 feet, that might be enough to injure you. About 300 milliamps, which is about 0.3 amp, third of an amp, is enough to kill you. Less than that, if you're grounded out properly and it goes directly across your heart, but 300 milliamps, if you ground out, would be enough to kill you. So that means a third of a coulomb per second. So that shows you just what a big amount of charge a coulomb is. So amperage is what is dangerous. All right. So what we're going to do now is turn over to page 525 in the packet. You have something called resistivity or resistance. If a river or a stream is just flowing along, it flows along. Maybe there's a bunch of rocks at a certain place and the water hits it and splashes up in the air. You have whitewater rapids. The rocks resist the flow of the water that kicks up all uh, the mist into the air, kicks the water up, makes it dangerous if you're going in a boat. That's kind of what happens with electricity. If you have electricity, a current going through something that conducts very well, like maybe gold, it kind of flows through it and that's it. Certain types of material, like if you've ever noticed, if you have an electric stove, have this metal that's in kind of a spiral and goes back down inside. The material this is made of has high resistance. A normal wire, like in your house, has low resistance. Just like when water flows through a smooth riverbed, not much is happening. The water goes, it does its thing. Electricity moving through low resistance, it moves through and it does its thing. Water moving through high resistance, you have rapids, you have all kinds of stuff happening. Well, if you move electricity through high resistance, it produces heat. So that's how an electric burner works. It's deliberately made to have a lot of resistance. The electric flow through it is resisted, and just like flow of water being resistance throws out kinetic energy in the form of the water spraying up all over the place, the electricity flowing through a high resistance uh, coil sets out kinetic energy in the form of heat. Normally, you don't want that. You want low resistance. You do not want the wires in your house heating up. That's where fires start. And that's how a fuse works. The old fashioned fuses, which they don't usually use much anymore, had a very thin piece of wire that was designed to melt if the resistance got too high. Melt, and then it would break the current. You'd have to put a new fuse in. Now they usually have breakers, which usually look like kind of a light switch almost. And if the current gets too high, the breaker flips up, has a little magnetic thing there. It flips up and kills the current. But the same basic idea is there. You don't want that high resistance because you don't want to build up of heat because you don't want a fire. But for the burner of the stove, you do want high resistance because you want to have heat to cook things. Well, the unit of electrical resistance is called an ohm, OHM, after the scientist who came up with that. And, generally we tend to abbreviate these things with the first letter. So the abbreviation for Newton is N, abbreviation for gram, G, so forth. Well, with ohm, you've got a problem there. Letter O would look like a zero, would it be bad to abbreviate it? So we use the capital Greek letter omega, which is the long O sound in Greek. So that's the symbol we use for ohms. And that brings us to Ohm's law. one of the most fundamental and basic things that you have in electronics, which says I equals V over R, where I current measured in amperes or amps, V equals potential difference measured in volts, you could just say voltage, R equals resistance measured in ohms. So this is one of the most basic and important laws that you have in electricity, electronics. Um, if any of you ever do go into electronics, trust me, you will see this up, down, sideways. You'll eat, drink, live, and breathe it. It's going to be extremely important because resistors are an important part of electronics in producing various kinds of things. There are things on a silicon chip in your phone or in a computer. There are very small things in the circuit that are equivalent to resistors or transistors, things like that. So it's a very, very important case. So one more thing I want to talk about, one more concept. Temperature variation. This is page 531, by the way. Temperature variation of resistivity. So, probably most of you all have seen a pinball machine. You know what it is. You have the pinball machine, you have the bumpers, and you have the little paddles that you control with the button. And you shoot the ball up, and the ball is falling. Now, if you're not hitting these paddles, the ball just falls down. You're not interfering with it. You're not, shall I say, resisting it. But if you're tapping these paddles up and down, you might knock the ball back up. Okay, so what does this have to do with temperature variation of resistivity? Here's a wire, and here are the atoms of the wire. And you know they're vibrating. That's what heat is. Now, electrons are coming through. That's what current is. The vibration of the atoms might interfere with the electrons occasionally, not so much. Heat it up, though. Now, atoms are vibrating all over the place, and they're going to interfere with the electrons getting through much more. So the resistance, R for resistance, increases. The hotter the wire becomes, the more resistance you have in it. Because the hotter it becomes, it's like the paddles. It's like hitting the paddles harder and harder and more frantically and more and faster. It's going to knock the balls around more. As a wire becomes hotter, its atoms vibrate faster, and that interferes with the flow of electricity. How does this apply to your life? Well, every time you go to the doctor, you have something called a thermistor, which means thermal resistor. A thermistor measures temperature by changes in resistivity. So you have a thermometer, and the tip of it is metal. And the thermometer's been lying in a case. So compared to your body, it's relatively cold. It's maybe at about 20 degrees Celsius, which is approximately room temperature. So you put it in your mouth. There you are, and there's the thermometer. Your body temperature is about 37 Celsius. As your tongue heats up the metal in the thermometer, or if you're at the doctor, they have one of those super high tech thingies where they put it in your ear. It heats up from contact with your ear, same basic idea. The probe, the metal in it heats up from your body temperature, absorbing heat from your body. As it heats up, the resistance increases slightly because the metal becomes hotter. Not a whole lot, but somewhat. And the thermistor measures that. And by seeing the resistance go up, it knows the temperature's going up. Then it goes beep, beep, beep. And hopefully it gives you a normal temperature around about 37, not a fever. That's how that works. Now, back in the day, when I was a kid, the thermometers were glass cubes filled with mercury. There's a chemical symbol for it. And mercury expands and contracts depending on the heat. And a problem, of course, is that glass can be broken and the mercury can get out. And mercury is very toxic, especially to children. They still made mercury thermometers right up into the late 80s, early 90s. Then they shifted to other non toxic materials, although that can still be a problem because it can still break and shatter. And nowadays, almost the only kind of thermometers you have are electronic thermometers because the electronics became cheaper and easier to make. And once it became possible to use that, using a thermistor is much, much safer than using a mercury thermometer of the old fashioned type. Okay, so this is the second part of this video. We have covered a lot of territory. And if you feel a little bit overwhelmed, that's understandable. The physics book that I'm doing this out of, it's what I used when I taught at Syrian College, used to be in Lexington. And I taught one course, Physics 3, which was one whole semester of nothing but electronics. So we went very, very deeply into this. So I am just touching your toes into the water on this. So if it seems like a lot of material, if you're basically grasping the concepts, pat yourself on the back. Because what I've been doing is selecting just the highlights from what would be a whole semester long class. So let's look on page 559 at the problems. And I think I just gave you like two or three or so. Let's look at number 3, problem number 3, Ohm's law. We said Ohm's law is I equals V over R, where I is the current in amps, V is volts, and R is the resistance in ohms. So number 3, it says you have a 120 volt toaster drawing a current of 8.0 amps, which would be way, way, way sufficient to kill you quite dead. And they want to know what is the resistance. Well, you go with Ohm's law. Well, in this case, you know the I. It is 8 amps, and you know the voltage, which is 120. All you need to know is the resistance. So I multiply both sides of the equation by R. That gives me Ri equals V. R is what I'm looking for. So I divide both sides out by I, and that gives me R equals V over I. Then people is plug and chug. 120 volts over 8.0 amps. And as luck would have it, that is easily done without a calculator. It's going to give you 15. And your unit of resistance that's okay, just ignore it. Volt per amp, the unit of resistance is ohm. So 15 ohms is the answer. All right. I think that covers everything I want to say on this. I hope this makes sense. If you have questions, as always, please feel free to ask. I will talk to you later, and I hope you have a good rest of the day.